Okay, now we are talking about enzymes. Remember, an enzyme is one of the functions of proteins and a major function. An enzyme is what we call a biologic catalyst. Now, a catalyst in all of chemistry is something that can speed up a reaction without being consumed in the reaction. It, in a fanciful way, can speed up a chemical reaction without being consumed. Catalyst is the mother term. In biochemistry, we can call it an enzyme. So an enzyme is a biological catalyst. Okay, we go further and we say that there are different classes of enzymes. Now, I'm just showing you these, so I'm not interested in you memorizing this, but there are different classes. Now, a commonality is is that anytime you see ACE, A-S-E, on the end of some chemical in biochemistry, it means enzyme. So ACE says automatically it's an enzyme. That's a generic thing, so that you'll know. Okay? Your types of enzymes, again, not interested. Okay, enzymes are proteins. There is a new exception. I like to be on the cutting edge, but we won't discuss it. We have found that RNA, one of our genetic S molecule type, can act as an enzyme, and that's called ribozyme. So in the past, it used to be all enzymes were proteins. Now there has been an exception that we have found some that are RNA, as a ribozyme. That's about all I'll mention on that. Enzymes govern the direction of all biochemical reactions. They take them down the path of least resistance. So think of a chemical reaction standing there, and it's got 5 different pathways it could go down. And all are equal, 5 different pathways. So it would just be hodgepodge as to which one it would pick. But if an enzyme was present that could do that, then the enzyme would lower the resistance on one of the pathways. So it would take that pathway. It would make the reaction go down the path of least resistance. So enzymes govern all of our biochemical pathways. That means enzymes govern the pathways of making triglycerides, of making carbohydrates, of making other proteins. They are the central entity. When you mess up an enzyme, a whole plethora of things can happen. Because suppose that enzyme is governing the direction of something, but what it's governing the direction of can feed into 5 other things. And then those 5 can feed into 5 more governed by another enzyme. So if you mess up the first enzyme, you will throw pathways off 20 steps down. As I alluded to, ASE at the end, that suffix means enzyme. Okay. I'm not going to read the history, but I'll just say this. It had to do more with the bread industry and other things, that they found that there was something in yeast that could make things go faster. And they came up with the term in yeast, enzyme. All right. How do enzymes work then? What they do is they lower something called the energy of activation. Now, you're going to have to go back to my ANP1 when I talked a little bit about thermodynamics. So here's a graph that I've made, no energy to high energy. So on this y-axis is energy. Here is time of reaction. Now, we have a reaction, let's say atom A plus atom B are going to molecule AB. Just go back and study the inorganic. If A plus B, the energy possessed by A and B, is higher than the energy, those are the reactions of the product AB, then there'll be a downhill reaction. This reaction would give off energy. We said that was called an exergonic. Go back, an exergonic reaction, because the energy would go away. Most would go away as heat, remember? Again, an exergonic reaction is spontaneous because it already has enough energy. But my point is, and I want you to pay attention to this, that even on this exergonic reaction, there's a little hump of energy it must go over. Kind of a hump of energy to get the reaction started. the energy of activation. So that hump is the energy of activation. That means even though this is exergonic, it still can't fall down the hill until it goes over that. So then how could you make it go over that? Or how could you make this get out of the way where the reaction would go quickly? That would be to take this hump down or to go over the hump. All right. Now, to go further. Even with an endergonic reaction, you still have a hump. But there's more of a problem. Because this little hump, you have this obstacle here is the one you have to overcome now. There is one there. So the point is it is an energy of activation, but this is the major one. This is non-spontaneous. Remember, in order to do this, you must bring in energy, and that's called an endergonic reaction. Now, what am I going to say is that energy of activation? It's back in my inorganic. It's really more of the collision theory. If you look back, is that even if two things are favorable for one another, they still must find one another, collide and everything I mentioned. So that energy of activation really falls under the auspices of that collision theory. Go further. What does an enzyme do to the energy of activation, that hump? It lowers the energy of activation. Now let's go back to the definition. An enzyme accelerates a chemical reaction without being, quote, consumed in the reaction. Accelerates a chemical reaction without being consumed. Now, if you came in, I'm going to go back to this slide here. If the enzyme came in and donated energy to this, it would gradually be consumed because each time it gave energy, it would lose some energy. So in some kind of way, it's got to do it without being consumed. That means it's not going to give energy and go over the hump. Okay? So we go back. If an enzyme donated, it would slowly be consumed. So what is it going to do? An enzyme lowers the energy of activation. In a fanciful way, it drops that hump. In a fanciful way, it drops that hump. So let's look at this slide. So here's that hump. But look what the enzyme is doing. Dropping the hump. Dropping the hump. In some way, it lowers the energy of activation. Okay? So how does an enzyme lower the energy? We must examine the construct of an enzyme. An enzyme is generally a long chain arranged in a globular fold. Two main portions. The active site. The active site is where the enzyme does its work. Then I'll say you have the rest of the site, which I'll throw my word and call it the structural unit. So it's like in your bathroom you have the sink. Assume the sink is the active site, and the other of the counter cabinet would be the structural unit. All right, we'll come to the cofactor coenzyme in a while. So here's kind of my little drawing, not a good one. Here would be a globular enzyme, and here would be the active site. That would be the structural unit. Let's ignore right now this area. So this would be the structure unit, and this right here, that area there, is where the enzyme would do its work. Here I'm looking at another one. Let's say a folded string of amino acids, and then you'd have an area where it does its work. Okay, let's go to this. An enzymatic reaction, the enzyme active site is where you are going to work on what's coming in. Now, I'm going to come here. What you're working on is something called the substrates. So the substrate or substrate, get that word, the substrate or substrates is a generic term for what an enzyme works on. The substrate or substrate, sometimes it's just one. That's why I keep saying substrate of an enzyme. Sometimes an enzyme just bends something to make it work, and it would only be a singular. When it finishes, you have made the product. So remembering reactants to product. Reactants, but when you involve an enzyme, the reactants would also be called the substrate or substrates. It's where the enzyme works on. What does this active site have? The active site has, I'm going to say, affinity, because what it can do is to pull in the substrate or substrates from the surrounding. And it has specificity. That means when it comes in, the substrates must have a certain shape that can in some ways congruently fit in to this active site. So the two things, affinity, which means drawing power, and a certain shape to come in. Okay? So here would be an example right here of substrates. This would be the active site. They would come in and fit, and then work would be done in some fashion to release the product. Okay. Here we go. The enzyme active site has affinity. That means drawing power for that. What causes this action? It has to do really with the aura groups. Remember the aura groups in amino acids? Remember this is folded string. And these aura groups would have some degree of pull on the substrate. Now here's kind of a commercial thing. If we look evolutionarily, there was a reaction out there that nature needed. The reaction occurred, but it was too slow. So an enzyme, through evolutionary trial and error, was finally developed to speed up the reaction. So the enzyme was created after the need for the reaction, which gives the enzyme specificity for that reaction. So these aura groups then would have been designed in that active site to specifically pull in that particular substrate. Okay? The substrates are just moving around by entropy. Remember, entropy is randomness of motion, and they would keep. But once they kind of swing past here, they would get drawn in. By them being drawn in, it would eliminate the atoms must find one another, because you would pull in the right stuff, all the molecules. And then they would have to sit in certain, just like buttoning your shirt. It wouldn't be any kind of way they could sit in this chair. They would have to sit in a specific pattern, which would then make them collide in the proper orientation. So you can read that. Okay. The enzyme has specificity. This specificity is accordance with shape. The shape of the active site is almost congruent with this. Now, almost, A-L-M-O-S-T. The old deal was known as the lock and key model. The new way is called the induced fit. The old was the lock and key. The new is what we call the induced fit model. Okay? The lock and key model said that you had to be the exact shape. Now, I often allude to in class, if it had to be the exact shape, let's take even the NBA. If the basketball hoop was exactly the same size as the basketball, you'd have to hit it dead center. The games would be a lot less in scores. The induced fit model says that it's kind of the shape, and when it comes in, it fits the shape. It's kind of like in clothing. Let's say you have a small, medium, or large, and it's kind of a fabric type that can stretch. Then the person puts it on according to those that are somewhat small, medium, or large, and it finishes the shape after you get in there. But you had to kind of be the right shape. You couldn't take a big person and put it in the small, expandable outfit. But then you could take several large people, put them in the large, and eventually each one, because it would congruently fit, if you can see. So the induced fit versus the lock and feed. So the new one is the induced fit. Okay, we're going to pick up in a moment with enzyme 2. This was enzyme video 1. We're going to do enzyme video 2 in a moment. Thank you.